Okay, we're looking at problem 15.11. Here's the problem. We have a beam considered to be massless or of negligible mass, and we have this 150-gallon bucket of water with a chain here and a cable there. If we isolate the problem into two free body diagrams, what we can do is see that the free body diagram for the bucket looks something like this. Tension 1 up, so Ft1 up, Fg down. The volume is this, and there are 8.34 pounds per gallon. Get a number here, sum of the forces in the y, tension up, gravity down, tension 1 is equal to this. Let you do the calculation there. Then if you do a free body diagram for the other body, and that would be the beam here, the forces we have are a reaction at the hinge up, a reaction at the hinge horizontally. Just to show you what I'm talking about here, there's a force up here and a force over here because of that axis being through the beam. We also have a tension back and to the left. We call that T2, and this is T1, the same one that we saw in the other free body diagram over here. So tension T2, T1. The angle theta here is the inverse tangent of the vertical length over the horizontal length that you see in this diagram. 3.13 over 6.35, inverse tangent, so you get an angle there in degrees. If you sum the forces in the x direction on this beam, you find out that F of Ry is one of the only forces in that direction. This has no component that's horizontal. This one also has no component that's horizontal. And this one is back and to the left here. Its component is negative Ft2 cosine theta. That's all equal to 0 because the beam is not moving. If you sum the forces in the y direction on the beam, you see Fry going up, and then Ft2 times the sine of theta going up as well. That's what that is right here. And we have Ft1 going down. And there's no sign on this or this one because those are strictly going up and down. If you look at the number of unknowns expressed here, there's actually 3 unknowns, as it says right over here. In other words, we don't know what the reaction in the y is, the reaction in the x is, or Ft2. And that means that we're going to need another equation to solve for the unknown. So the sum of the forces in the x and the y are not enough to solve this problem. So what we can do is sum the moments about this point right here, the origin. That's the point of rotation for the beam. I'm calling that m sub o, so I'm calling this my origin. The thing about picking this point here is if you look at the moments due to Fry and Frx, they end up having 0 moments. The reason that is because the way that you calculate moments is you take the lever arm times the force times the sine of the angle between them. But in these cases, because these forces are applied at the origin, there's no lever arm. So R is equal to 0 for these two, and therefore their moments is equal to 0, even though the forces are not 0. In other words, you can't push on this axis right there and cause a rotation. You have to have the forces being applied at a distance from the point of rotation in order to cause a moment, also known as a torque. Now if you look at this force right here, you'll see that what it causes is a counterclockwise rotation. You put your fingers here, use your right hand, put them along the beam, curl your fingers back toward Ft2, and you'll see the thumb comes out of the board. So that's why you have a positive sign that's right here. The lever arm is the length of the beam L. The force is Ft2. And then you also see the sine of the angle here, sine of theta. And you have already found theta by taking the inverse tangent of some lengths up here. If you look at the rotation caused by this chain pulling down on it, you look at the lever arm L right here, you see T1 acting down. It's at the distance L from the point of rotation, and the angle between these two right here is 90 degrees. So that's why I have at the end here 90 degrees. Also have a minus sign here because if you put your right hand, your fingers here at the origin and extend them along the beam and curl your fingers back toward Ft1, your thumb is into the board, so therefore it's minus. If you then move this term right here over to the other right-hand side of the equation, you get something like this right here. So the minus sign goes away because you're adding this whole thing to both sides. Then you see that the L's cancel out right there and right there. And that means that you can solve for ft2 right here, simply by dividing both sides of this equation by sine of theta, where theta was determined up here. All right, so then you'll have f of t1 times sine of 90 divided by sine theta. This will allow you to find the tension in that top cable that we had seen previously right here. That tension right there. So there's two tensions, T1 and then T2. The last part of the problem says that assume that you have a safety factor of 3. All right, now let me pause the video right now to show you where that safety factor equation is. All right, the safety factor is equal to the yield strength of the material divided by the stress that you allow to happen in that part. Okay, so going back over here and trying to calculate the safety factor for this thing right here, what you're going to do is write down the safety factor equation right here. I'm using SF for safety factor. It's equal to the yield strength of the material, which I assume to be, let's see, oh, yes, steel. But they go ahead and tell you what the yield strength is right there. So 35,000 psi is the number that goes in the numerator over here. Now all of this that I'm showing you right here, that's the definition. I'll bounce over there and show you that again. Safety factor equals yield strength divided by allowable stress. Now back to the solution over here. That's the definition. The allowable stress is defined to be the force that you apply divided by the cross-sectional area. You take this right here and you put it in for sigma and you get that right there. Then you see that if you multiply top and bottom by A, you have the cross-sectional area here times the yield strength divided by the force. As we've discussed in class, the cross-sectional area is pi r squared or it's pi d squared over 4. I then plugged that in there and I just noticed right here that I forgot a 4, I think. Let's see. It should be pi d squared over 4 times yield strength in F. I'm going to pause the video, add a 4. Okay, and there's the 4 right there. Let's focus on this end result right down here. You know what, let me see if I can highlight that in red. All right, so there's the end result here with the diameter of the cable in there. That's what we're looking for right over here in this spot. There's a yield strength and the force applied. We know what the safety factor is. We also know that that is 3 in that case. So safety factor is 3. That means if we solve for D2 right here, we'll be able to get the diameter. So what I've done here is I pulled from right here, going down, get an arrow on this. All right, so I'm taking the D2 right there from that equation. So from right here down like that, okay? And then that means I'm going to take the 4F and move it from the denominator here to the numerator over here. So I still have the safety factor right there, safety factor times 4F. And then I'm going to take the things out that's not D squared and divide both sides by that. So I have pi yield strength, pi yield strength. Then I simply take the square root. It's supposed to be a square there. I simply take the square root and I find that if I take the safety factor, which is 3, times the force being applied, and I think that is going to be, oh wait, yeah, here's the force that we're applying, because it's the beam that we're talking about up here, the cable, not the beam, the cable that we're talking about here. So this is FT2 right there. There's pi yield strength, as we said over here in this problem right here, 35,000 psi. All right, hope that helps. See you soon.